Hello AP Calculus students, my name is Aiden Kelly. I'm a senior graduating mathematics major at Manhattan University, and for today's proof I hope to show that we can evaluate the limit as x goes to 0 of sine x divided by x. I'm glad I'm speaking to AP Calculus students, as this proof would be far too complex to explain to any other level of high school mathematics. I hope to show that this limit exists using L'Hopital's rule, which you may or may not be familiar with, but basically it states that if three conditions are met, we may apply the limit to the derivative of the numerator and the derivative of the denominator. So first in this video, I start out by defining f of x and g of x. Specifically, f of x is the numerator, sine x, and g of x is the denominator, which is x. Notice that f of 0 is sine of 0, which itself is 0, and g of 0 is simply 0. This is the first condition of L'Hopital's rule, specifically that the limit of the initial function is of the indeterminate form 0 divided by 0. As both functions approach 0, they approach their value at 0, which then becomes 0 divided by 0, meaning that this condition is met. The next condition states that the derivative of both functions exist. Now, given that you are in AP Calculus, you understand that the definition of a derivative, in basic terms, is the limit as h goes to 0 of f of x plus h minus f of x divided by h. As I write this down on the board, you will see that f prime of x equals the limit as h goes to 0 of sine x plus h minus sine x divided by h, and the derivative of g of x is the limit as h goes to 0 of x plus h minus x divided by h. Now I can show the algebraic breakdown, but being that you are in AP Calculus and I am in college level analysis, we know that the derivative of sine is simply cosine, and the derivative of x is simply 1. This can follow algebraically, and I leave that to the viewer to do themselves. While I write, I hope to explain that L'Hopital's rule is important as it allows us to evaluate limits where previously they would seem unapproachable. Also, the third condition for L'Hopital's rule is that g of x, or g prime of x, cannot be equal to 0, as this will lead to a divide by 0 error. Here we have shown it as 1, and for those clever among you to have spotted that 1 is not equal to 0, this condition is also upheld. This allows us to apply L'Hopital's rule, specifically to say that the limit as x goes to 0 of f of x divided by g of x is equal to the limit as x goes to 0 of f prime of x divided by g of x. Of course, it's not always x goes to 0. It could be x goes to any constant or any function, but in this case we're working with the limit as x goes to 0. It's important to note that given the technical powers of AI and its rapidly increasing development, an artificial intelligence would be able to create a much more elegant proof than I ever could. However, you're stuck with me. So let's get on to the proving. We now know that the limit as x goes to 0 of sine x divided by x is equal to the limit as x goes to 0 of cosine x. As I erase, I will explain the analytical definition of a limit, which I will use to show that this exists and evaluate with. Basically, the definition of a limit for an analysis student is that when for any epsilon greater than 0, there must also exist a delta greater than 0, such that when 0 is less than the absolute value of x minus c, which is here 0, which is the constant that we are approximating for, is all less than delta, that implies that the absolute value of f of x minus the limit of f of x is less than delta. Here, from your time in pre-calculus and AP calculus, you will know that cosine of 0 is 1. So we will use this as a guess for our limit. Here I am writing out the definition. So now I invite us to recall from our time in pre-calculus two main identities. The half-angle identity for cosine, which states that 1 minus cosine x is equal to 2 sine squared x over 2. We know that the absolute value of cosine x minus 1 is equal to 1 minus cosine x. So that allows us to apply this. And also, I invite us to recall the sine inequality, which states that the absolute value of sine of t is less than or equal to the absolute value of t itself. We will use this to develop an inequality that will allow us to show the implication from x being less than delta to the absolute value of cosine minus 1 being less than epsilon. As you can see from what I'm writing, the absolute value of cosine minus 1 is equal to 2 sine squared x divided by 2, which is less than x squared over 2 by that inequality from before. This allows us to choose a delta equal to root 2 epsilon, so that algebraically we can cancel out the square root and we can cancel out the 2, and we'll have that the absolute value of cosine x minus 1 is itself less than epsilon. So now ultimately, using the definition of L'Hopital's rule, I hope that you see, as I see, that the limit as x goes to 0 of f of x divided by g of x is equal to sine x divided by x, which is equal to the limit as x goes to 0 of cosine of x, which we have shown is simply equal to 1. Therefore, by L'Hopital's rule, the limit as x goes to 0 of sine x divided by x is itself 1. Now, I would just like to give a brief aside towards ChatGPT's proof, which does not attempt to use L'Hopital's rule, and instead much more elegantly applies the squeeze theorem to evaluate the proof, to evaluate the limit. Ultimately, if given enough time, I probably could have came up with this myself. However, ChatGPT came up with it in half a second. This goes to show the value of AI in that as it ever increases in strength and intellectual capabilities, it will find more elegant solutions to problems faster than any human ever could. Thank you.